today's presenter, and it's my pleasure to introduce Javi DeLa Cruz. He is the VP of Engineering at Xperi Corporation. He leads the design, simulation, and assembly teams as they develop and introduce new technologies. He was previously at eSilicon, where he led the engineering operations team, and prior to that, he was at Stats and at R&D and at MACOM. Javi holds a Master's of Engineering degree from Boston University, so let's welcome Javi.
All right, great. Hi, everyone. Thanks, Ira, for the introduction and for inviting me to speak here for everybody. And I'm glad you guys came over to listen. So I'd like to talk to you about is what we see as truly enabling technology for next generation devices. And we'll talk a little bit about the trends. We'll talk a little bit about what a big problem is on the horizon. And we'll go through an actual case study showing you performance, cost, from a unit and NRE standpoint, area impacts, all these sorts of things. So we worked very closely with folks at eSilicon, and they were able to provide me actual numbers. Going through the folks at eSilicon were able to leverage their pretty deep design infrastructure and be able to figure out different trade-offs and what the impact would be on the area, performance, speed, all sorts of impacts that relate to what we're going to show you here, and we'll go over that. So for the agenda, let's cover what's really in the horizon. What's the problem with compute? Why can we not get much faster? CPUs haven't changed in speed since, mid-90s. And for very good reason. You can't process data any faster than you can access it. And you just have a certain distance between processing and memory, and you just can't get much faster than that. We'll cover a little bit about what this very fine pitch technology confers as a benefit. And when I say very fine pitch, I'm talking about single-digit micron pitch, not the hundreds of microns that you have with flip chip or thermocompression bonds. And you'll see that it could be lower power, higher performance, reduced area, and what's not listed here is have a very positive cost impact, which we'll show you. This leverages existing production-proven technologies, Zybond and DBI. If you're not familiar with that, I'll cover it briefly. There's a little bit more detail on it. There's one issue of a chip scale review over by where I was sitting. If someone needs to have a little bit more detail on the background of DBI, because it covers a little bit more detail in that magazine article. One of the challenges to overcome, one of the biggest challenges, is to really have the mindset of designing in 3D as opposed to stacking of 2D designs. Many of the designs that exist currently that label themselves as 3D are really just stacks of 2D designs, and because of the way they're conceptualized and how they're interconnected. And we'll show you one of the many ways to actually design in 3D. One of the very key issues that comes up on the horizon, and I've seen this referenced many times in recent trade shows, is this barrier, this big wall on the horizon of reticle limits. And reticle, if you're not familiar with it, it's how big of a field you can expose on a wafer with a stepper. And that generally denotes the largest die you can make. Now, there's ways around it, but it's challenging and expensive. And then we'll go through the actual case study I mentioned earlier. So let's start off with just imagining a die. And on that die, you have a block. That block needs to speak to other blocks. So we'll just consider the block to be 1 millimeter by millimeter. So if you consider all of the beachfront that you have going along the 4 edges of this block, assuming you have 10 nanometer manufacturing, you have about 12 signals per micron. Now, this is in the middle layers. That number doesn't change as you go to 7 and 5 because the wires don't scale. Transistors can scale, wires don't scale. And it's just, you can't impact it's too much of an impact on the capacitance and resistance to change them. So this translates pretty well through all future nodes. So you have, for that block, assuming you had 4 middle layers, you can double it, say 200,000 connections per square millimeter in that square millimeter. But that's really what you can accomplish, because all those signals only have so much beachfront, that periphery of that block to make connections to other devices. That's still a pretty big number. Now, if we were going to say in that same block, assume that you had conventional thermocompression bonds at 40 micron pitch, you can fit 625 of them. How does 625 compare to 100,000 or 200,000? There's no comparison, and that's one of the big barriers with 3D. When folks are talking about these new technologies in 3D and all, it's all well and good, but at 40 micron pitch, you're not going to accomplish very much. It forces you to design things in 2D, and we'll cover that in a little bit more detail. But what if, instead, you had the ability to have 100,000 to 1,000,000 connections in that square millimeter to the next die up? Theoretically, having a higher density of connectivity from one die to the next than you can even within the same die. That's huge. That's huge, and that's going to have a big impact. So, how do you connect these things together? What's the interface you use? Well, the punchline, as you can see already, is no interface. But let's kind of walk you through it. So, depending if it's 2D or 3D, you really got to think about how far do I need to drive this signal. If you're in 3D, you're only driving a signal vertically about 1 micron or 2 microns. Whereas if you're on the same die, you might be driving it millimeters. So you need more drive strength to drive it a certain way. But if you're going from die to die, you generally have a lot of load there. So you need to drive the signal quite a long distance. And that's what a lot of folks are doing right now with their chiplet approaches. They're using these very powerful drivers to drive a very short distance, and they're building in all this inefficiency. So there's existing interconnect styles that are really meant for connections within a die. There's no reason you can't use that to go from die to die. In fact, you can use them even more efficiently because you don't need to add in all the repeaters and extra flops needed to drive a signal a longer distance. You're going a shorter distance. So there's a certain efficiency built in by being able to do that. So let's say if you take a piece of paper, and the piece of paper has all these connections, from point to point on there, you just fold it in half. Mathematically, you get a 30% net reduction of the average connection between any 2 points. That's with no planning. No EDA tool will work like that, right? EDA tools are much better than that. But on the other extreme, if you deliberately have things that would be laid out in a die, on the same side, but you have to have lots of them to get around, you might travel millimeters, right? But if you ended up putting things directly over each other, you're only traveling a couple of microns. So think of, instead of going millimeters, you go microns, and what that impact has on the speed you can perform at, the power of all these connections. So we'll discuss that shortly. But before we do that, let me just give you a little bit of background on what these technologies are. So Zibond and DBI, two technologies originally developed by Ziptronics, if you're familiar with that. Ziptronics was acquired by Xperi in 2015. And ever since then, we've been focused on developing the die-to-wafer process, because the wafer-to-wafer process at that point was already pretty well matured and licensed. So in Zibond, the original applications in this were image sensors. In fact, both of the one or two of these technologies are in your pocket right now, or in your hand. If I don't see anybody using their cell phone, luckily, so it's likely in your pocket. So it could be used in various devices. It could be used in, most likely, in your image sensor and MEMS device and lots of other devices as well. But with Zibond, if there were connections between them, you would just end up bonding dielectric alone and then having a via afterwards, via down to a connection in the first wafer, a connection in the second wafer, and then a little piece of metal in between to make your connections, which is great if you don't have that many connections. And this has served the image sensor market well for quite a long time. We talk about DBI. DBI confers a greater benefit, and that is you can get to an extremely fine pitch. So you have your connections already on the surface, and so you have a mix of a dielectric and your connections, and when it's polished to a very flat surface, they can be bonded together. No adhesive, it happens at room temperature. You just go through a subsequent anneal, and all these connections happen simultaneously across an entire wafer or across dies to a wafer. And this has been proven down to below a micron. Okay, so it's been demonstrated, it's been talked about by various companies. Some have shown 1.6, 1.0. In volume production right now in image sensors, I believe the number is 3.8 micron pitch currently in volume production. So, like I said earlier, wafer to wafer has been mature for quite some time. But die to wafer was something that was a challenge with this for quite a long time. And we've had this technology in-house at Xperi since 2015, and we focused our entire team on this to really develop this process. And we're at the point now where it's ready for showtime. And so it could be die to wafer, and then if you add more die on top of it, we refer to that as die to die. Okay. So the process for assembly of die to wafer is different enough that we call it DBI Ultra. It's on the same basic principle, but there's a few changes of steps and additional steps to be able to enable this technology, really to overcome the challenges of particulate, because you have a small particulate in a bonded surface. It's not going to bond very well. You've got the edge condition of the die after you've sawn it apart. So all these things need to be accommodated. And we have this process now, and we have been working with our customers to be able to bring it to market. I think if you've been to other presentations, we've shown an HBM-like stack with 20 die high. So nobody needs 20 die at this point, but it's certainly doable. So we've demonstrated that. There's some pretty cool images there. So with that background, let's go ahead and talk about a looming problem in the industry that it's being addressed differently by different companies, and that is reticle busting. Reticle busting really comes down from Moore's law coming to a slow death. Despite some folks say it's not going to die, others say it's dead already, but it's we all know, we've been in the industry long enough. You could predict how much a die would shrink when you went from 0.13 to 90 nanometer. Well, how much does a die shrink when you go from 10 to 7 or 7 to 5? Guess what? It doesn't, right? So why? Because wires don't shrink. You can have smaller transistors, but you end up needing more space around them. And if anything, your die may actually grow for the same number of transistors, which poses a massive problem for our industry. You want to be able to cram more functionality into a given die, and you have an upper limit of your die size. Well, guess what? You can't. So different folks have come up with different strategies to accomplish this, and you've all heard about chiplets. AMD has been discussing their EPIC Rome for some time, and the way they accomplished this was they ended up they abstracted the CPUs as chiplets, and there's 8 of them shown here, and they ended up having an interconnect buffering die in the middle of them, and they all communicate with this device and go out to the outside world, and you have a net greater silicon area than a reticle. That's all well and good, but you've got to drive signals now that were on the same die now across a package substrate. And how are they doing it? Well, all these guys are doing a very similar thing, and they use some form of a modified PCI Express interface to be able to do that. So your signals get really serialized, and you drive them across fewer wires to get from point A to point B, which, that serialization and all that stuff takes up area. It burns power. It adds latency. Okay, these are all problems, but I guess there's problems that are smaller than the fact that you can't fit anything larger than a reticle. Okay, let's move on to somebody else. Nvidia has their solution. It looks pretty different. It's pretty interesting looking. And they end up making these chiplets, and they have every chiplet able to talk to every other chiplet in their neural network SIP device. Well, once you get to 16 of these chips, about half your power is spent on pushing bits from die to die. So your incremental benefit of adding more of these chiplets tapers off pretty quickly. You can't really get into that large of a network, but it gets you past the limitation of what you can fit on a reticle. Okay, so you're trading one problem for a different problem. Another one that's here you can see is this Intel Radeon, where they've had the CPU separated from the GPU and talking to an HBM interface over here. They're separated mainly because these are two very hot devices, and you need to be able to cool them, somewhat separately. And then they also come from two different manufacturers. In fact, it comes from this guy over here, the GPU. Long story short, though, this is a way for them to be able to add more functionality because you can't fit the GPU with the CPU. It just won't fit. It's too big of a die. Okay? So all these different approaches really to try to overcome that challenge of a reticle limit. So let's talk about a problem. Let's talk about a problem even bigger than what these CPU guys were trying to accomplish, and that is the networking space. The current state of the art is a 12.8 terabit per second switch. It's a full reticle size currently, and that's what's shipping in production now. That's like the state of the art. Well, every generation you've got to go 4x that amount of capability. 51.2 terabits per second will not fit in a reticle. In fact, it needs to fit in about 4 of them. So in a switch, all these die need to have extremely high bandwidth between them. So it poses a huge, huge challenge to the networking landscape. So again, working with eSilicon on this problem, they've identified, like I said, 51.2 terabits requires about 4 reticles. Okay, and to the outside world, this device is going to have 512 lanes of 112 gigabit per second SerDes. This is an incredible amount of bandwidth off of the package. But even to handle all that switching, you've got to handle at least that much between the die. Okay, that's a huge challenge. Having that much SerDes to talk between the die is a major impact as well. So I'm going to show you a couple of different ways to skin this cat. In all of them, they're all going to have about the same amount of memory and logic. What's going to change is the interface that we have between these devices and the packaging format. Okay, but they're all going to have the same amount of logic. And yeah. So first scenario, option A. We take your package substrate and we stack on, so we have two different 7 nanometer designs, a bottom layer and a top layer. So between these two die, you have a very large field of DBI interconnects. But in between them, you've covered this in two different ways. Okay, so option A, and here's the decoder ring, and this is the tricky part. So you got to focus on these next two slides, otherwise the following slides are going to be very confusing. So I tried to make it kind of clear. So option A and option B, the difference between them is how we connect them together. How do we connect this stack to that stack, that orange arrow? And one solution is to use an ultra short reach SerDes, which is the same solution that likes of Intel, Nvidia, everybody else is all using to be able to connect these die together. That doesn't require an interposer. Okay. Now, or the other solution is to use an HBI interface. An HBI is just like HBM, but you're connecting two logic die together as opposed to a logic to memory. So it's an interface adapted from the standard HBM interface. Pretty small, very fine pitch. And because of that, it requires an interposer. Okay, so I haven't shown the interposer in this one, so I'm making a note. The one you're viewing here is option A. Option B would be the same thing, but you'd have an interposer directly between the die stacks and the package substrate. So those are two of the options we're going to consider. The next one we're going to consider is we start with a package substrate, and in this case, I'm showing you option D. And we're going to put 4 die together. Now this is a very large interposer. It's an interposer that's 4 reticles large, really meant to interconnect these 4 large die together. And the way they talk to each other is if you take any 2 die, they can talk to each other through that one interface that's in between here. So you can't go in the diagonal, which is one flaw with this. You can only speak to your neighbor that you share a beachfront with. Okay. So this case, the stitched interposer that was analyzed because it's commonly available is 65 nanometer. That's what was considered. So 65 nanometer, that's the current technology that, if you look at any technology with any device with an interposer, that's what they're using. Okay. Now, in the same regard, option C has no interposer because option C is using this USR interface. So Option C is the one that very closely matches what these other folks are doing with the EPIC Rome and the Nvidia neural network. It's using chiplets with no interposer, but using this USR SerDes to connect all of them together. So we're going to analyze that as well. Lastly, and this one is more of a novel approach, and what will be used is the base die is active. It's not an interposer. So what we have is a die that has 9 of the same exposures. These exposures don't talk to each other. Okay, they're independent. And the pink area is the only area that's active. Everything else is just a pass-through. It's just a TSV going from above it to below it. And on top of that, we'll put the 4 die. So it's only the active area that's in the center that connects those 4 together. That's the only one that's being used. So your yield on this active base die is extremely high because of this giant base device. Only a very small area of it is actually true functional active logic. The rest of it is pass-through. Luckily, 28 nanometer has gone down in price dramatically, so it becomes pretty cost-effective to do this. Okay, so this is the part I want to make sure everyone's pretty clear on. So it's, I'm going to go back just to cover it one more time because it's pretty important. This base die is active. The pink area is the active portion. That's where your logic is. The dotted region, these are just pass-throughs, and you have 9 exposures. There's no stitching here whatsoever. Just 9 exposures, and when you make your wafer, you only choose to use the saw street on every 3rd saw street. So that's the way it ends up looking, right? There's nothing connecting these 2 together. Okay, so then when you place them, now when you put the die on, only this one in the center is the one that's connecting all of these die together. Okay? Okay. So, in other terms, we're going to show that using DBI Ultra in this sort of scenarios may be able to give us some yield improvement because we're not going to be stuck having to go to a scenario of stitching reticles together. Once you do that in an emerging node like 7 nanometer, you can count the number of good die per wafer with a hand and have extra fingers to spare. So it's not going to be good. So in this scenario, in options A and B, we do have DBI between the 2 die. Okay. And options C and D, we don't have any DBI at all on option C because there's no interposer. We're just putting 4 die directly onto the package substrate, which is exactly the baseline that we want to consider in what, Intel EPIC and the, AMD EPIC and Intel device as well as the Nvidia neural network. Okay. Now, but if you do have an interposer, what we considered was using DBI for that. And then lastly, we have the connectivity here, these 4 die to this active 28 nanometer device. And all the connectivity happens through this center location. Okay? So just to show this center location here, of the 9, just the center one was considered. What can also be considered is the ones that are here on the center of each side. They can be utilized, but in this analysis, we didn't do that. Just for the sake of time, we focused on just having all the connectivity through the center. So you can get even more efficiency, but it just took more time to be able to have multiple active regions. So what are the results? So we consider latency. Now, when we did the latency analysis, we only considered latency between the adjacent die, not the diagonal, because in some cases, the diagonal was not possible. So it'd be difficult. So we'd only considered the ones that are next to each other all the way around. So HBI has inherently lower latency than USR. And why is that? Well, a USR spends a lot more time serializing. And HBI is a much wider interface. It's 1,024 data wide, or a USR might be a by 8 or a by 16. And so all that extra serialization takes clock cycles and adds latency. And in the scenario, the last one, option E, which we call them native interconnects. Actually, let me go back to that because I don't think I emphasized that adequately. The connections that we have between these two are the native interconnects, and that is the same interconnect that is used within a die is connecting from die to die. There's nothing different. There's no, just think of the connections between these two die to the die look like they're on this. They haven't left the die yet. That's what they look like. So it's the same type of interconnect you would have within the die is used to connect them through a bridge. So with that, the latency compared to our baseline. So if you consider the baseline to be option C, you have a 79% drop in latency. I'm sorry, I go back? Okay, sorry, with power. All right, so power's first. So yeah, 79% drop in power. So just to remind you, we have some of the scenarios here if you need to remind yourself as to what options A, B, and C are. Or you have another key up here as well. But only the lateral chip-to-chip interconnect, we're not using the diagonal, was considered. And the native interconnects, as you can see, by far consume the least amount of power. So when you have 4 full-size reticle devices performing networking operations, they get hot, very hot. It's a challenge. There's no question as to why data centers are locating themselves next to power plants, and that's just the way that these things are trending. So let's take a look at latency now. Latency has a very similar benefit. Again, HBI is inherently lower latency than USR just because of the less serialization that needs to occur. And you have this 57 drop compared to our baseline from what's similar to what the industry is doing right now and talking about in trade shows. 57% better latency. If you can access the data you need to process faster, you can process more quickly. Frequencies can start to go back up again because you're no longer limited by I can't go any faster than I can access what needs to be processed. Okay, so that's a huge benefit. So now mask NRE. Compared to our baseline, let's talk about this first. So options A and B require 2 7-nanometer tape outs. That's a lot of money. So they are dramatically higher. Okay, so we're not considering those to be a baseline, but we have from option A to option E, you've got a significant drop, 37% on NRE, because it's almost cut in half. But you've got to add in additional design and tape out for that the bridge wafer. Option C was the simplest because it's really just a 7-nanometer tape out and nothing else. So that's kind of the baseline that we have right now. In option E, it's only marginally more because you've got to add that 28-nanometer tape out plus design costs. But you get a massive benefit in unit cost. Okay, and it's not immediately obvious as to why. So I'll explain why in a moment. But by eliminating these interfaces, whether it be a HBI interface, which an HBM interface is roughly about 6.1 by 3.5 or so, going all the way around the die. That's pretty large. That's a large amount of silicon area. So the cost there for this, yeah, okay. So you have, so you have the total area improves on option E, really, because you've eliminated these very expensive area real estate interfaces along the edge. There's nothing there. So it shrinks the die dramatically. Because of that, your yield goes up. So when you're at the reticle, you're at that asymptote, or actually you're past the asymptote of that exponential curve, and any incremental area you pay dearly for on yield. And by reducing that dramatically, you see this. So it's not 77% less area, but the area benefit that's there confers that benefit of 77% from a cost standpoint, which is dramatic. Dramatic and very attractive to folks in the networking space dealing with these challenges. So to summarize, the most compelling solution that's in here is E. And E is the one that eliminates the interface. It uses the same interconnect to connect the die together that are within the die normally to connect a block to another block. So you can see a summary here of the benefits. Now again, there is an additional mask cost one time, and then this could vary based on the technology that you're using. And again, I want to just make sure I thank eSilicon for being able to provide a lot of this analysis. So in summary, a couple of questions that I've been asked in the past, let me just go ahead and address them initially, is, why aren't people doing this already? Well, die to wafer is fairly new. And when you design your die to go with a native interface, you've got to design it to only work that way. So there's a bit of a risk of the unknown. It's not the same way we've been doing things for 30 years. It requires a brave new approach. Now, in other industries like image sensors and MEMS and those, it's mature and there's no problem in going down this path. In the SoC realm, where you're dealing with these really large die, there's big risks here, and on the die design. So introducing something new is kind of a scary thing, but this is a very temporary problem. The new technology, DBI Ultra, where it's now high yielding to be able to put die on a wafer at very fine pitch, is that's fairly new. I think it's been about a year now since we've publicized this. And the design cycle time for a lot of these is longer than a year. In fact, it's quite a few years. And the nice thing is you don't need to worry about what next standard you're going to use to connect between these die, because you're going to use the same interconnects that you have within a die. And what's key is the challenges, or what you're able to get by going and thinking in this 3D approach. You're able to get price, performance, area benefits that you don't have any other path to go with. If you're trying to stitch these die together, yield is going to plummet and pricing will skyrocket. So this provides an approach where you can actually have a much more cost-effective solution. Okay, I want to just acknowledge we have work done by Ferran Matorel and Prasad Subramanian in this work. Okay, any questions?
Thank you, Javi. Questions?